Hello everyone, welcome to today's class. This is Teacher Simon taking you through Cambridge International AS and A-Level Mathematics Paper 4-2 for October-November 2023 for questions 1 to 4. Question 1. A block of mass 15 kilograms slides down a line of greatest slope of an inclined plane. The top of the plane is at a vertical height of 1.6 meters above the level of the bottom of the plane. The speed of the block at the top of the plane is 2 meters per second, and the speed of the block at the bottom of the plane is 4 meters per second. Find the work done against resistance to the motion of the block. Now here, I'm going to use the energy method. It is the easiest to use here. My sketch here, remember in mechanics, you have to learn the art of sketching because it solves a lot. So this is the resistance here. That we are looking for, and then this particle is moving down here. It has a driving force, okay, that is taking it down there. Then here we are supposed to they are saying that the speed of the particle or the speed of the plane at the top is 2. So let's say u here is 2 meters per second. So meaning here it has kinetic energy because there is speed, and there is also potential energy because there is this vertical height generated here. Okay, that's our h. And then here, what do we have? Actually, this vertical height is given as 1.6. We don't need to know the angle since we know the h here, okay? Because usually the h is equal to the d here, okay, sine of the angle, but we don't need it. Now, down here, the speed is it 4? Yes, 4 meters per second. I can call it the v because it is sliding down, okay, slides down. So this will be the final. So that means here there is kinetic energy, okay. And then work done. Remember, we are using the energy method. Work done by the driving force. Work done by the driving force or the applied force. Okay, then minus work done against resistance. Work done against resistance is equal to the change in mechanical energy. Change in mechanical energy. Now, since this one is just sliding downwards by itself, there is no driving force, okay? The dF is equal to 0 because this is free fall, okay? It's free fall. So this one is going to be 0. Then minus work done against resistance. That is the one we are looking for. So let me represent it with WR. And then change in mechanical energy. Mechanical energy is equal to the potential energy plus the kinetic energy. And potential energy is mgh, where h is the vertical height, and then kinetic energy is a half mv squared. Now we get the final minus the initial. So the final is here, which where we just have the kinetic energy. There is no potential energy because relative to this position here, there is no vertical height. So we are going to have a half times m, which is 15, then v is 4 squared, then minus the initial, we are having potential energy, which is 15, times g, which is 10, and then the height is 1.6, then plus the kinetic energy, which is a half, then the m is 15, times the speed here is given as 2 squared. Now, minus WR here shall be equal to 16 divided by 2, 8. Then 8 times 15, that is 120. Okay, 120. Then inside here, what do we get? We have 15 times 10 times 1.6, and then we add 0.5, because 0.5 times the 15 times the 4, so that is 270. So inside here we have 270. In fact, let me just write everything here without the brackets. That is 270. When we subtract, minus WR shall be equivalent to, that is 150, negative 150. So that means that work done against resistance, if you divide all through by the negative, is going to be 150 joules. Okay. Question 2. The diagram shows a smooth ring R of mass m kilograms threaded on a light inextensible string. A horizontal force of magnitude 2 newtons acts on R. The ends of the string are attached to the fixed points A and B on a vertical wall. The part AR of the string makes an angle of 30 degrees with the vertical. The part BR makes an angle of 40 degrees with the vertical, and the string is taut, meaning it is very straight. The ring is in equilibrium. Find the tension in the string and the value of M. So if the system is in equilibrium, that means that the vertical forces, the resultant in the Y is 0, and also the resultant in the X is 0. So the forces acting on R, let me draw a straight line here, vertical, and then I'm going to make it dotted so that it doesn't interfere with the rest, dotted. And then this particle here, being, it has a mass, okay, m kilograms. So I'm going to put its weight here, which acts downwards, so it's going to be mg. And then I'm going to extend this one here, this horizontal line. Let's say we extend it there. And also I'm going to make it dotted, okay, such that I can find the horizontal components of these ones here. So these particles, this particle here is on this string, so it is going to experience a tension. Remember, tension is always pulling away from the object. So it is also the same tension here, since it is the same string. It is just threaded through, okay? Then, since this one is 30 degrees here, and this one is 90 here, that means this one is going to be 60 degrees, okay? And then this one here is going to be 50 degrees. Okay, I'm going to resolve this force here. I can put it here, like as if I'm going to detach this one here, okay? And then I put it here. So when I do that, I'm now opening this angle, and opening is a sine. So I can put here T, then sine of that 60 degrees, okay? Which is the same as cosine of 30, okay? If I close this one here like this, when like I'm detaching it from here, then I'm putting it here. So I will be like closing it here, and then it is going to be giving me T cosine. So, and it will be facing up. So you see, that is all the same. Then this one here, I'm going to, remember here I have 50. Okay. Then I can open the 50 up. Okay. When I open, it is a sine. So this one is going to be T, then sine of 50. You see? And then when I put it here, I close the 50, then it is going to be T. Okay. It is going to be T cosine of 50. T cosine of 50, which is the same as T sine of 40. Okay. And then remember this one here, we detached this from here and we did that. So we opened the 60. Now we can close the 60 by putting this one here. So when we close, then we shall have T cos of 60 degrees. Now, what do we therefore have as our now forces? Since the system is in equilibrium, that means horizontally, the ones that are going this way, that we are having only 2 newtons, then it is equal to these ones that are going this way. So we shall have T cosine of 50 degrees, then plus T cosine of 60 degrees. then this one will be equivalent to 2. Cosine, of course, now here t is common, so I'll have cosine of 50 and then plus the cosine of 60 degrees, which is equal to t. So meaning t is going to be equal to 2 over cosine of 50 then plus cosine of 60. But cosine of 60 is actually a half. So putting all of this in the calculator, what do we get? 2 divided by cosine of 50 then plus cos of 60. So it gives us 1.75. So T is equal to 1.75 newtons. That is to 3 significant figures. Just like that. And then let's go to the vertical forces. So resolving the forces vertically, what do we have? So the ones going down, we have mg and t sine 50. And then the one going up, we are having only t sine 60. Okay, so t sine 60 is equal to what is going down is t sine 50 and mg. T sine 50 degrees and mg. Remember m, yes, m is m, and then the g is 10. So already we have gotten the t. So I can bring this one this side, and then we get this is sine of 60 here, then minus the sine of 50. Okay, factorize out the t. Okay, then we divide by 10. This one will give us the m. Now our t, I'm going to use the exact, this one here, not just the 1.75, because it wasn't an exact value. So this is cos of 50, then plus cos of 60 is 0.5. Let me just write this as 0.5. That is the t. Then here you have sine of 60 degrees minus the sine of 50 degrees, then out of the 10 here. That will be our m. So putting everything in the calculator here, what do we get? 2 into sine of 60, then minus sine of 50. Okay, then close the brackets, and then we go down. 10 has to multiply with cos of 50, and then we add 0.5, then we close. Then this one will give us 0.017 and the rest of those figures, but to 3 significant figures, that will be 0.0175. So m is equal to 0.0175. You can put as kilograms. So that is that. Question 3. A block of mass 10 kilograms is at rest on a rough plane, inclined at an angle of 30 degrees to the horizontal. A force of 120 newtons is applied to the block at an angle of 20 degrees above the line of greatest slope. There is a force resisting the motion of the block, and 200 joules of work is done against this force when the block has moved a distance of 5 meters above the plane from the rest. Up the plane. Find the speed of the block when it has moved a distance of 5 meters up the plane from rest. Okay. Now we need to first resolve the forces. So close this one, close this 20 here. That one is going to be a cosine. So we can have 120 cosine of 20. Okay. And then this one here, we shall have the normal reaction, and we can also have the 120 sine of the 20 degrees. Remember, closing is cosine, and then opening it up is sine. Okay. Now, since this is a rough plane, that means we have the coefficient of friction. And since this one is going up, that means the frictional force is acting downwards. Okay. That frictional force, which is mu r, I can just say Fr, the frictional force. Then here we are having, of course, mg, the cosine of 30 degrees. And also here we have mg, the cosine of, the sine of 30 degrees. So there was mg here, which tilted the same angle when the plane was tilted to that angle. So now, find the speed of the block. So I'm going to use the energy method. I can use our SOHCAHTOA here, because by the time it comes, let's say it has moved up to here, okay? This is my point of reference, and it has moved 5 meters, okay, up the plane. Then here, it has kinetic energy, okay? It has kinetic energy because it is moving at a certain speed there, and then potential energy because there is generation of the vertical height. You get that? Now, no, actually this h is supposed to be here. This is my point of reference. So I'm going to put my h just there. It's everywhere here. I'm looking at that point from at that point where it has moved from, then to go up. So then here it is starting from rest, so we don't have kinetic energy. And since this is our point of reference here, then we also don't have potential energy, okay? Now, this is 30 degrees, and this is h, and this is 5. So sine of that 30 is equal to the opposite over the hypotenuse. So meaning h is going to be 5 sine of 30. Okay. Now, using the work energy principle, work done by the driving force or the applied force minus work done against resistance is equal to the change in mechanical energy. And remember, mechanical energy is potential energy plus what? Kinetic energy. Potential energy is mgh. Kinetic energy is a half mv1 squared. Okay. So the driving force or the applied force is this one here. A force of 120 is applied to the block, okay, at an angle of 20 degrees to the horizontal. So the applied force is now this one, the horizontal component is the one that is going to take the particle up there. So we shall have 120 cosine of 20 degrees, then times the distance it is going to move. It is 5, because remember, work is equal to force times distance. Then minus work done against resistance was given here as 200. So I'll write 200, and then change in mechanical energy, I just have the final here. So kinetic change in mechanical energy, I just have the sum of these two. So the kinetic energy is a half, then times the mass, which is 10, the speed, we don't know it, and it is the one we are looking for, then plus the mechanical energy, I mean the potential energy is m, then g, and then h. H is 5, then sine of 30. So what is left is now to find v. 12 times 5, that is 60. Then there is another 0 here, then cos of 20, and then minus this 200 here. Then here we shall get 5v squared, and then here a half, because sine of 30 is a half of 100 is 50. So 50 times 5, that is 250. So meaning, if I want to find my v, making it the subject of the formula, is going to be the square root. So now we first take away the 250. So minus 200 here, then minus 250. Then we divide by 5. Then that is when we take the square root. So what will be the answer here? Square root of 600 cosine of 20, then minus, I think that will be 450. Then down here we shall have a 5. So we get 4.77 at 3 significant figures. 4.77 meters per second to 3 significant figures. As simple as that. Question 4. A particle P of mass 0.2 kilograms lies at rest on a rough horizontal plane. A horizontal force of 1.2 newtons is applied to P. Given that P is in limiting equilibrium, find the coefficient of friction between P and the plane. Okay. Now, this is a horizontal surface, so I'm going to put my particle here. Then this way we are having a force of 1.2 newtons. And then we have the normal reaction because it is on a plane. Normal reaction is there when a particle is on a plane. And then there is its weight, which acts vertically downwards, so 0.2 g. And then there is frictional force here, which is mu r. Okay, mu r. Then, so resolving, since there is no vertical motion, this simply implies that r is equal to 0.2 g, which is actually 2 newtons if you multiply by 10. Okay, and then horizontally, since there is no movement, it is in limiting equilibrium. When they say limiting equilibrium, it means that it is on the verge of moving. So that means the frictional force is there acting on the particle. So as you are applying this force, the frictional force is also resisting that motion. So we shall have mu r, which is equivalent to 1.2. So our mu is going to be that 1.2 divided by r, which r is 2, and then mu becomes 0.6. And then part B, given instead that the coefficient of friction between P and the plane is 0.3, find the distance traveled by P in the third second. So I'm going to look at 3 things here. I want you to look at my sketch here. I have this particle here, okay? It travels a certain distance here in the first second, okay? In the first second. Then it is, let's say, here in the second. Sounds weird, eh? Second. Then it comes here in the third second. Okay? Now, of course, we know that this is 0.2 g. Then there is our r here. Then there is this force 1.2 newtons. And then there is mu r, so 0.3 r, because mu has been changed. Okay? All right. Now, we are going to use forces. So F is equal to ma. Okay? So we need to find the acceleration. 1.2 minus the mu r, 0.3, and our r is equivalent to 0.2 times the 10, okay, which is equal to 2 newtons. So times the 2 here, the mu r, then is equal to, the mass is 0.2 times a. So what is the acceleration? This one is going to be 1.6 minus 1.2 minus 0.6, that is 0.6. Then if we divide by 0.2, acceleration is going to be 3 meters per second squared. Okay. Then from there, if I want to find the distance traveled in the third second, I will look at the distance traveled in 3 seconds. Okay, I can call it S3 in 3 seconds. Then I subtract the distance traveled in 2 seconds. I will call this S2. So I get S3 minus S2, as simple as that. So in 3 seconds, okay, in 3 seconds, remember S is equal to ut plus a half at squared. So what is the distance covered here? The S3 is going to be, since the particle is starting from rest, that one will be 0, then plus a half. The acceleration, we have gotten it as 3, and then times 3 squared. So that will be 27 divided by 2, okay? 27 over 2 meters. And then in 2 seconds, S2 is therefore going to be equal to, still here we have 0, then plus a half, times the acceleration is 3, and then 2 squared. And then this one gives us 3 times 4, that is 12, divided by 2, we get 6 meters. So distance traveled in the third second is going to be equal to the 27 over 2 minus 6. 2 times 6, that is 12, then 27 minus 12, that one gives you 15. So 15 over 2, that is 7.5. So we shall have 7.5 meters. That is the distance covered. So that has been it for this first part of the paper. Thank you so much for watching. May God bless you. If you find the content very helpful to you, kindly like, share, and even subscribe. See you in the next video.